Can you start?
Yes, we are ready. So the first speaker today is Boron Chen. So please.
Okay, hello everyone. I'm Paulo Chen from NTU, and my topic is the path tracking of mobile robot in crops. And this is also my reference. Okay, so this is my outline. I will first introduce what this paper want to show us and modeling the plant in this paper. And then the controller and control is mean the goal we want our robot to do. And model reference adaptive control and adaptive PID control and physics control is the three different controller mentioned in this paper. I will briefly explain what those controller did, and then I will make this paper have a computer simulation and result, and the final is the conclusion. So let me start my introduction. What's the difference between mobile robot moving in a plantation or in a factory? I think this is the first question we need to know. So let's see the picture in the left. This is the mobile robot move in a factory. So you see the factory ground is very smooth, and so when the mobile robot walk on it, it may not shake very loudly. However, when the mobile robot move in a plantation, you see the soil is very rocky, so the robot will shake, and you may not make your mobile robot do your task brilliant or something. So we want to conquer this question. And the second question is, how do we design our controller to make robot perform as well as we want in the crops? So we see in the previous question, the factory will move brilliant, but in crops may not. So this paper mentioned three different controllers to make the mobile robot move in a plantation just like we want in the factory. So this is the three different controllers mentioned in this paper. Okay, third, which is the best? I think this is the most important question this paper want to show us. So I will expand in the conclusion. Okay, so this is the modeling and description of a mobile robot. Because it's a differential mobile robot, all the input is the omega R and omega L. You can see the red frame. Omega R means the right wheel angular velocity, and omega L means the left wheel angular velocity. With these two input, we can get the V is a matrix. V present the velocity and angular velocity. It's all in the robot frame, robot coordinate. So we want to know the relationship between robot coordinate and Cartesian space. So we multiple rotation matrix, and S of Q is the rotation matrix. It will transfer the robot coordinate to the wolf coordinate. So we will get a Q dot. Q dot means the X dot, Y dot, and theta dot in the Cartesian space. So X dot is the X coordinate speed. X dot is the X coordinate speed in the Cartesian space, and Y dot is the Y coordinate speed in the Cartesian space, and theta dot is the angular velocity. It's just the same in the robot frame. So we get our kinematic model, and then we will use it to accomplish our task. Our task is to move to a point. So you'll see Q is our point we want to go, and C is the mobile robot center. So how do we know our mobile robot move to our point? So let's define two state variable. Those two state variable is d and phi. D means the distance between Q, distance from C to Q. So, and phi is the angle of it. So if d and phi converge to 0, we know that our mobile robot move to the goal we desire. So this is the paper task. This paper wants the mobile robot move like this red line. So it's the path it wants its robot to move in the crops. And so we see the control screen of the mobile robot. The reference path is the previous, just like this. This is the reference path. So, and you get a reference path, you will get an arrow of x and arrow of y. It means the arrow, x coordinate arrow and y coordinate arrow between mobile robot and your goal. So F controller and the position controller will get the right wheel speed and the left wheel speed. It's reference. So you need to send voltage to your motor. However, you may not reach the goal, the speed you want. So it have the inner loop to make the speed to reach your desire. So it's the inner loop function. Okay, so next, we will get the omega R and omega L. So we use encoder to get the omega R and omega L. We'll get the, after the kinematic model, we'll get the next position of this mobile robot. And we do this for a loop. And this is the model reference adaptive control mentioned in this paper. So it's the online system ID in the mobile robot. So this is the equation is the previous. It is the relationship between the velocity and angular velocity with the coordinate with the Cartesian space, and the red frame is what we desired before, and the blue frame is the uncertainty we want to conquer. So we use the adaptive law. So we will get the A0 and A1. So we will let our mobile robot move like we previous do. And second is another adaptive controller. And it's just like the same, but it has a different structure. So it adaptive loop is want to get a KC, TI, and TD is made. So it will get KC, TI, TD to this proportional, integral, and differential parameters. So we want to get the parameter from the equation. So, and okay. The last is the physics controller. It's just like the machine learning. So we get the ED and E5 so we will get the V1 and omega 1 and so on. So all we need is a lot of data. So if we have a lot of data, we just need to input ED1 and E5 we don't know, and the physics controller will get the velocity and angular velocity just to our mobile robot. So our mobile robot can move to, can reach the goal we want it to do. And okay, this is the simulation and result from this paper. So the red frame is the best, and the blue frame is the worst. And we use 3 different index to compare these three different type of controller. So we will see that the error of X, model reference adaptive control do the best in the error of X, and adaptive PID control done the best in the error of Y. However, it done the worst in the error of X, and the fuzzy control done the worst in the error of Y. Okay, so, and this is the path tracking result. In the reference is the significantly deviation from the path. I know you cannot see it clearly, so I frame it for you. And this is so we'll see that the PID adaptive control down the worst in those cases. So, and this is the talk result. So it means the motor in the simulation talk in time. And the red arrow is the model reference adaptive control, and the blue one is PID adaptive control, and the green one is fuzzy control. And this is an enemy I made. So we'll see the red arrow first. So we can see the red arrow move, relative move. And next is the blue one. The blue one, so we will see the enemy. And the blue one is move a little worse than the red one. And the last is the green one. It starts from here. And so we'll see that it moves very worst. And so it's the conclusion. And so the first question is, are those control methods accomplish the test? Yes, I've seen both, all of these accomplish this task. So the second question is, which have the best result? I think the model reference adaptive control had the best result. So the third question is, why is it the best? So I think the reason why it is the best is because it has the smooth talk, and it has the best error of X and so on. So it has the smallest error and most smooth torque. Okay, so this is my conclusion. Thank you for listening.
Okay, any questions or comments from NTU? Yes, please.
Thank you for your presentation. Can you define what is good performance, what is good moving performance of this robot?
You mean that the mobile robot moves the best, or?
Yes.
Oh.
Can you define?
I think this paper defined it because it has the smallest error and of X, and the torque is very smooth. I think the torque also oscillate very loud. It may hurt our motor. So I think the model reference adaptive control is the best.
Okay, thank you.
Any more questions? Yes.
Okay, thank you for your presentation. Do you think it is possible to mix three kinds of method together to make the best control method for that?
I don't think so.
Okay, thank you.
Because it's the three different structure, so it's hard to make it together. This is my opinion.
Oh, I mean is for example, like the fuzzy control has the best for performance on moving straight, and for the curve path that probably the PID has the best performance. So if that they are moving different routes, they can use the different method.
Oh, I know what you mean. But I still don't think. I'm not sure about it.
Okay, thank you.
Any more? Perhaps Ian would like to make some comment.
I'm just curious about the result. Is it only in the simulation?
Oh, yes, it's only simulation.
So, what? Because does the paper show the parameters they use in the simulation? Because that would affect the result. For example, the nominal parameters of the mobile robot and the variation of the parameters. Things like that, you know.
It did not mention it on the paper, so I'm not really sure. I'm not really.
Okay.
No.
I think the result is still not very convincing. I mean,
I'm still confused about it.
Yeah, I also thought about the conclusion because there are different parameters will give the different simulation results. For example, the fuzzy. Can you go to fuzzy slide? I don't know what kind of shape function they used. They use the triangle or they use different and will be affect their simulation results, I think.
This paper just mentioned it used the type, so it did not tell the detail about it.
Okay. Okay, thank you. So let's conclude from NTU Q&A. How about University of Tsukuba?
Thank you for your presentation. I just want to ask, I'm not sure if you mentioned it, but in the first part, but can I know like what is the practical application of this research?
We want to know is the papers this paper want to show us or the question? Okay. So you want to? Okay. So the question we want to our mobile robot to tracking a path we want in the plantation or in the crops. This is the goal this paper want to show us.
Yeah, like, I mean, that's obviously like the point of this research, but what other application can you think of this technology? Like, why would they actually make a study about this? Would this be important in the agriculture sector or in some other fields?
I think the problem is using those kind of control. We can move our mobile robot in the uncertain environment, either in a Mars or something.
Okay, thank you.
Okay, thank you very much for your presentation. So your introduction says that what the difference between mobile robot moving in the plantation or the factory? That means in the running on the field or in the factory. So how about the result? Is applicable for the field too?
Sorry, I didn't hear it clearly. So, will you please?
Yeah. What is the major differences between field and factory, in your opinion?
Oh, you mean in a factory and in the crops are different or?
Yes. Yes.
So in a factory, the environment is simple and the ground is very smooth. And in a plantation or outside, you make your mobile robot walk on the soil, and the soil is very rugged, and so it may shake a lot. And so you did not control your mobile robot brilliant. You did not control it well.
But so recently, so the sensing system is very advanced, and the controller speed is very high speed too. So I think the almost same situation we can build by using such kind of technology when we apply this technology on the field. Yeah, that's my opinion. So how about your opinion?
So in your plantation, the disturbance is very large. So when you use a simple controller, your mobile robot might move horrible. It might struck your vegetable or something. So you need to use different type of controller just like this. So you can make the mobile robot move just like we want. If you use the simple controller, is might slip in the soil, so you cannot control it. Do I reply your question?
Hey, thank you very much. 大丈夫です。
Sorry.
Oh, that's all from University of Tsukuba.
Okay. How about the Kyoto University?
Go ahead.
Thank you for your presentation. Let me ask one question. What do you think is the biggest advantage of fuzzy control?
Can you say it again? I'm sorry, my listening is poor.
What do you think is the biggest advantage of using fuzzy control?
Oh, you mean the advantage?
Yes.
Oh, I don't think fuzzy control have any advantage. Because it's a little like AI, so you need a better hardware for this. So I prefer model reference adaptive control. That's my opinion.
Thank you.
Okay, that's all from Kyoto. Thank you very much. It's
Okay, so let's finish the presentation Q&A for the first speaker. So from the second speaker on, all the three other speakers were from Kyoto University. So Professor Kondo, please.
Yeah, thank you very much. Can you change the sending material? And the first presenter, get ready, Ueda-kun. You changed your computer. Today we have three presenters, Ueda, and it was Higashi, but changed into Kim Junbin, and finally Tamura. Those three. And during waiting this time, let me talk about the next week schedule. Next week, December 23rd. Pira Sensei may give us, supposed to give us guidance for writing abstract. But just before that, one more presenters we have. The problem was Kim Junbin was out of country during his military service. So that's why his presentation was skipped before. And today's presenter switched by Kim Junbin. And today's presenter Higashi may give you a present next week, just before Pira Sensei's lecture. Okay, ready? Okay, Ueda-kun, go ahead.
Hello everyone. I'm Junpei Ueda, and today I'm going to give a presentation about my research detection of rotten chicken eggs by Pseudomonas fluorescens. First, I introduce my research background. And there are various types of abnormal egg from farm. Then it is detected and specific one is removed. At first, there is eggs which has abnormality on shell, such as shell with sturs like this and cracks. And like this and dirty egg is removed by using image analysis, and this cracked egg is removed by sound technology with this small hammer. And there is also eggs which has abnormality inside egg. For example, this broad one and light color one. And for example, and this egg which has abnormality inside the egg is removed by using transmittance light technology. Rotten egg is one of the eggs that has abnormality inside egg. And rotten egg is caused by the infection of bacteria. Bacteria or molds through tiny pores and cracks. And as this graph shows, and black rotten one and yellow rotten one is shows big color change. So we can detect it by transmittance light. However, there are another type of rotten eggs. It is rotten egg by Pseudomonas genus. In spite of the infection of Pseudomonas, there is no change in color and structure, so we cannot detect it by transmittance light. Because of this egg is an industrial problem now. And of course, there is some problem in this rotten egg. And Pseudomonas fluorescens is representative Pseudomonas genus that causes this rotten egg. And Pseudomonas is unusual cause of disease in humans, but usually affects patients with compromised immune system, for example, patients on cancer. And so we cannot eat eggs infected with Pseudomonas. And infection by Pseudomonas fluorescens is worried, especially in liquid egg factory. At liquid egg factory, cracked eggs and dirty eggs from grading and packing center are also used because they use only the content of egg. These not clean eggs are likely to cause a higher possibility to infect. In addition to this, Pseudomonas fluorescens can multiply even at low temperature. Although most of bacteria cannot multiply at low temperature. So once this egg infected with this bacteria is used, whole tank in factory is infected. From this reason, we need to detect this rotten egg before breaking this egg. And Pseudomonas fluorescens has properties that they produce puberine, which show fluorescence at low iron level. This photograph shows the left one is rotten one and right one is normal egg. When we see this picture, there is no change in color and yolk height, but when we eliminate this 2x, only Lawton X showed fluorescence reaction on albumin. And previous study also showed fluorescence, previous study shows fluorescence pigment that Pseudomonas fluorescence produce has peak at excitation rate 400 nanometer and emission rate 490 nanometer. When we measure only medium, and they show very low emission rate, but like this, when the Pseudomonas genus multiple at medium, they show fluorescence, they show strong 490 nanometer. And another study showed that fluorescence spectrum of intact egg. In this this graph shows that fluorescence spectrum of intact egg, and one is infected white egg, and two is normal white egg. And as this graph shows, white Lawton egg has peak at 535 nanometer, but this differs from the result of only pigment, as I showed at here. When we measure only pigment, and they show peak at 490, but when we measure intact, they show peak at 535 nanometer. So from these studies, I decided my research objective and goals. My research objective is to know why peak differs from only pigment to intact egg. And to achieve this objective, I conducted 2 experiments so far, and detailed fluorescence data about fluorescence Lawton egg and fluorescence change of egg component in Lawton egg. First, our team tried to know more precise Lawton egg peak by using fluorescence spectrometer. We used one white egg got from company as material, and Pseudomonas fluorescence multiplied in albumin with yolk was injected. And 11 days after injection, I measured fluorescence spectrum. And in this experiment, we wanted to know inside of the egg, not eggshell. So like this, I changed detection point. First, I compared these 2 measurement way. First, I set detection point at on eggshell, and second, I put detection point at inside the egg. And this is the result. And when we compare 2 types of measurement way, there is apparent difference. Shell showed no difference like this, but when we measure inside the egg, there is big difference between Lawton eggs and normal egg. And we can know the peak are seen at 400, 480, and excitation rate 430 and near 500 nanometer. And this means fluorescence by Pseudomonas fluorescence. And as a second experiment, I conducted fluorescence change of egg component in Lawton egg. This objective of this experiment is to know what component contribute to intact egg. And measurement item is like this, and I measured Lawton eggs, intact egg, and only albumin, and only yolk, and only shell. And as a control, I measured only normal eggs, intact egg, and only albumin, and yolk, and shell. And this is the result. And we can know the peaks of growth side means the Lawton eggs EM, but intact eggs EM and albumin's EM shows almost same shape, and this means intact eggs peaks are almost come from the albumin's peak. And this is a result of shell and yolk, and there's no big difference between shell and between normal one and Lawton one. So both of these graphs shows fluorescence spectrum of excitation rate 430 nanometer. And intact egg has peak at 5 fluorescence. Intact egg shows the peak at 530 nanometer, but albumin shows the peak at near 500 nanometer, and so peak differs. And this means result I got this time is same as previous study. And from this I had two hypotheses for why peaks are different. And first, maybe there is absorbance of shell. When the excitation rate is come from device, and shell will absorb this light, and also the fluorescence and the emission rate that albumin showed are absorbed by eggshell. And second one is absorbance of yolk. Yolk has also high absorbance, so they absorb excitation rate and also emission rate from albumin. And this is my future plan, and I will try some combination, for example, yolk with albumin and shell with albumin, like this. And also, this time I measure white eggshell, but as you know, there is some color in eggs, and they show different fluorescence data. So I'll try another color of this rotten egg. Thank you for listening.
Thank you for your presentation. I'm Tonyo, and I want to ask two questions. The first one is about how do you prepare the rotten eggs as your experiment sample?
And this time I got sample from collaborator company.
Oh.
And but I sometimes make it by myself. And before culture at medium, before I pseudomonas fluorescence at medium, and then I make a hole with a pin to egg and make a hole, and by syringe, and I measure it to egg, and then maybe 3 or 4 days later, and each egg becomes rotten. Yeah.
Does it mean you are cultivating pseudomonas?
Yes.
Right?
Yeah.
Thank you. And the second question is about how often the rotten eggs occur in the egg production process.
Okay. Actually, I don't know the precise answer, but this rotten egg by Pseudomonas genus is I cannot find any good data, but maybe very low. So, but not only eggs, and another food has also this problem by this Pseudomonas genus. So not big, but we should care about it. Yeah.
Okay, thank you.
Presentation, and I want to know where or when do you want to detect these?
Okay. So I don't know the situation of another country, but I heard that in Japan, and eggs come from chicken farm are first and sent to GP center, that grading and packing center, and then it is up there, and some technology are used like this, and so and same time as this, maybe we should detect this rotten egg, I think.
Possible to detect the fluorescence.
I hope so. Yeah.
Anyone else? Fine. Okay, thank you very much. That's all from Kyoto. Next would be NTU, please.
Questions or comments? Yes.
Hello. I just had a quick question about the bacteria. Do you think that we can adapt the experiment for other bacteria, like Salmonella?
Actually, I focus on only Pseudomonas, and as I mentioned, this Pseudomonas can multiply even at low temperature, but Salmonella cannot multiply at low temperature, like 2 degrees. So, and actually, all the time I do this experiment, and I preserve egg at low temperature. So maybe there is no possibility to multiply other bacteria.
Okay, thank you.
Any more questions or comments from our NTU? Okay, there's a conclude Q&A from NTU. Thank you.
Okay, Tsukuba, please.
Hello, thank you for your presentation. I was wondering if you could use the same method on other products, like maybe meat products or other eggs other than chicken eggs?
So I don't know in detail, but I think there are some possibility of detect some bacteria or some chemical product to detect it by fluorescence. Yes, I think I don't search about it, but maybe there is technology like that. Yeah.
Thank you.
Thank you for your presentation. I have a comment and a question. For the comment, I think in the title slide and in other slides, like you use Pseudomonas fluorescens, right? I suggest that you use a lowercase letter, a small letter for the species, because usually it's a big problem like when you're doing presentation. And for my question is, since here in Japan we eat a lot of food has raw egg, right? So can you tell us about the bad effects of consuming egg with Pseudomonas fluorescens to humans?
The people for advice, and if we consume this egg by Pseudomonas genus, and actually for normal people there is no problem, but as I mentioned, there are some people who has compromised immune system, and for those people, there's some possibility of become some sick. So yeah, actually for normal people there is no problem, I think. But as you know, maybe bacteria boost the egg quality decrease. So this detect of this bacteria is, I think, important.
So do you think here in Japan, there are a lot of cases of people actually consuming eggs with bacterial infection like Pseudomonas fluorescens?
Sorry, I don't know this the situation now. So yes, sorry, I cannot answer its question. Sorry.
It's okay. Thank you very much.
Thank you.
That's all from Tsukuba?
Okay.
Fine.
That's all from Tsukuba.
Okay, thank you very much. Good discussion. Interesting to me. I'd like to move to the next presenters. Thank you, Ueda-kun. Kim Jun, please. Ready? Right.
Hello, my name is Changbin Kim. Today I'm going to present a theme called Mobile Sensor Localization and Navigation using RF Doppler Shift. I'm currently doing research on the location of robots using sound in the lab. And in this presentation, I'm going to explain a paper that tracks the location of robots using Doppler Shift. In the background of this paper, the need for a location tracking method instead of GPA can track location and to solve this at a low cost. Problems include the size and cost of the GPA and poor tracking of the location indoors or in the woods. In addition, location tracking of mobile architectures uses optical encoders and sound sensors and laser rangefinders, etc. The smaller the size of the mobile architecture, the more difficult it is to implement this compact machine. Therefore, when the transmitter sends an ultrasonic wave, the receiver sends an ultrasonic. The receiver calculates the position of the transmitter based on arrival time and arrival time difference per transmitter, arrival angle, and receives signal strength. In this experiment, the robot is tracked by the principle of D-track using the radio interferometer method and RF Doppler shift. In other words, the robot position is tracked by the Doppler shift interferometer. We use multiple fixed receivers and passive fixed transmitters and master mobile transmitters. Master and assistant transmitters send pure sine waves and slightly different frequencies. The interference of these two signals occur, and at a given time, two receivers measure the frequency of the signal. Doppler shift, which occurs when a robot with a transmitter moves with respect to an observer, tracks the rover's position and speed and direction of a travel. Due to the regulations of the terrain, the robot may be out of defined orbits. In this case, Doppler shift frequency data is used to measure and correct the position and speed of the robot. There is measurement noise because of using low-cost hardware, but after filtering, the angular velocity of the wheel of the robot is corrected. In this study, Doppler shift data is used as feedback to control the mobile robot. And implement localization and navigation algorithms in a control loop that can convert this data into position and velocity vectors. That is, the position can be measured while compensating the angular velocity of wheel of the robot. The experiment is carried out using fixed position receivers and fixed position assistant transmitters and the master transmitters on the robot as shown. Periodically, the robot synchronizes with fixed receivers and fixed transmitters, then giving the receivers time to receive signals from the transmitters. In the figure, the dotted line isn't the laser pointer. No pointers. Such like a dotted line. This indicates the radio waves of the transmitter, and the arrow indicates the direction of movement of the robot. And the receiver measures the signal and then sends speed, position, and direction information to the controller on the robot. The controller then corrects the specified speed, position, direction, and other errors. The modification process is shown in the figure. The controller controls the robot's angular speed and speed, and the track passes Doppler shift frequency data to EKF. The controller controls the robot's angular speed and the speed of the wheel, and then the D-track passes the Doppler shift frequency data to EKF. The EKF then sends an estimate of the current velocity and direction to the controller, and repeat this process. The actual experiment was conducted with the robot attached to receivers and transmitters and controller and master transmitters. And EKF is as shown in this picture. This is the EKF model on the robots. Each sensor was at a height of 1.5 meters above the ground, and it was outdoors without obstacle as shown in the left picture. It's because of think about the obstacle effect. And as shown in the figure, experiments are carried out with 5 fixed receivers, as you can see in these 5 receivers, and fixed assistant transmitters and master transmitters attached to the robot in here. There are 3 steps to experiment. The first step was 30 meters straight running with no feedback, and second, drive 30 meters straight with D-track system feedback. At last, 90-degree rotation after 15 meters straight run with D-track system feedback. The result is as shown in the picture. The first step is like this one, and this is second, and this is third. The setup one showed almost no error in speed, but this is because the speed has not changed since we adjust the speed. However, due to the wheel slip and irregularities, the errors of location and heading were large. In setup 2 and 3, the errors in heading and position were small. However, there was a slight error in speed because of the focus was on the correcting the direction rather than the modifying the speed. by shortening the cycle time of control loop, strengthening the controller seems to solve the speed error problem. All of these experiments were performed 100 times and resulting in results shown in this table. If you look at the total in the table here, you can see that the feedback is applied at the speed of 1 Hertz. The results for the experiment were satisfactory, they say, but by using cheap hardware, there was a problem that is it was not possible to know exactly what interference frequencies could vary in successive time step of around 65 Hertz. Figure 7 shows that the unacceptable measurement of the interference frequency. In this case, the error range was 0 to 65 Hertz and the average was 26.41 Hertz. In order to minimize the multipath effect, the experiment was conducted in an outdoor area without obstacles. But if there is an obstacle, there will be a problem, I think. In conclusion, the position tracking technology of the mobile sensor was satisfactory through the interference of the Doppler shift. The result is a 30-meter orbit with an average error of 1.68 meter with a feedback of 1 Hertz. References is as follows, and thank you for listening.
Thank you for presentation, and please show me the 8th page number 8. Yes, and you mentioned the setup 1 position error and heading error is big, but setup 2 and 3 position error and heading error is small.
Yeah.
But my question is, how do you judge the error is big or small?
Because with the as I mentioned that the setup 1 is the without the feedback, we set the track, and 2 and 3 has a feedback. But as you can see, we in this lecture they say that they focused on the vectors, not just the speed. So as you can see in the here, they fixed the velocity of the direction. As you could you see without feedback, just they going straight, maybe not straight, but to wrong places. But with the feedback, they maybe go to the right places. And this part is just because of the problem of the speed, because they just focus on the direction, not the speed. So if they make a lower speed, then it will not be the problem, I think. Okay, thanks.
Thank you for your presentation. My name is Hiroki Tamura. And could you give me an example of the mobile sensor?
Mobile sensor?
Yes. What mobile sensor is?
Actually, what we said, the mobile sensor is maybe something that we can locationing or tracking the robot or some things, maybe just like a GPS. Yeah, but actually this so there's many like a sensor for tracking the location, but such like a GPS is high cost and not such good for tracking in the small places because it has a lot of error. Sometimes it have a 50 meters error in some places. So we tried to find cheaper and we mean a low cost. And actually my final goal is to find some sensors that we can track some robots in the greenhouses. But GPS is the problem in the greenhouse, and such a kinds of So,
thank you very much.
Anyone else? Okay, that would be all from Kyoto. NTU next, please. Question.
Okay, any question, comments?
Thank you for your presentation. Is this paper mention about what plan he want to control?
Excuse me?
The plant this paper want to control.
The final goal is to control the robot, but it's just the paper is for the tracking and feedback the robot. So actually we can't control it at the same time. We want to make it automatically. So
okay, I see. Thank
actually
you.
we cannot control. Excuse me?
I said thank you.
Any more? Yes, please.
Which field can use this technique?
Take what?
And which field can use this technique?
As I said at the question from our school, that the final goal is to using it in the greenhouses, but the GPS system have a heavy and very high cost, and it has such a lots of errors in greenhouse status. So we try to use another system to locationing and tracking the robots. So this is the maybe basic research about the tracking the robots in the greenhouse system. So actually this research has, they do not think about the obstacle effect, but maybe this research can be the basic research about the locationing or tracking system in the greenhouse, I think.
Okay, thank you. You want a question? Okay, go ahead.
Thank you for your presentation. I'm wondering if this technique can apply in the greenhouse. Is it possible to guide the UAV for this system?
Excuse me, guiding what?
UAV, the flying robot.
Yeah, maybe such systems can be used in the drone also, but I don't know actually how it does, because we also need transmitters and such like a mic and speakers we need also, but with the drone it can't be possible, I think, because the height would be much more higher than such places, because we settled it as a 1.5 meters higher than the ground. But if you're using the drone, I think it wouldn't be possible, I think. Okay. Because also drone have such a big noises, and it can be also the problem of this system.
Okay, thank you.
All right, thank you. That's all for NTU. Thank you.
Okay, thank you. Next would be Tsukuba. If you have, please. Any comments? Okay. So, for example, that the letter is very small on the figure or something like that.
Thank you for your presentation. As Sensei said, yeah, some of the texts are kind of small, so I suggest to make it bigger next time. And then at the conclusion, in your conclusion, you mentioned that the error size was around 0 to 65 hertz, right?
Yeah.
And then you also mentioned that it was maybe because of cheap hardware. Were you able to make your own experiment that includes also like the recommended hardware for detecting the path of robots?
I think it can be possible, but my objective is making it less than 20 millimeter, the 2 centimeters. So I think it would be possible with my research. Actually, this is not my research, so.
Okay. Thank you.
The basic research of my research, so okay, thank you.
Okay, that would be all.
Yes.
Oh, thank you very much. All discussions. We'd like to next presenter would be Tamura-kun. Get ready.
Hello, my name is Hiroki Tamura, and today I will talk about this contents. So, this experiment was conducted in Indonesia. It's because in Indonesia the fluorescent imaging was not familiar to choose to separate the rotten agricultures such as fruits or vegetables. So today I will talk about the case in Indonesia. Today's content is these four. First is introduction, and next is method. The third is the results and discussion, and the last is conclusion. Then first introduction. Then do you know what the fluorescence is? And first I'll explain about the system of the fluorescence. When a substance gets the energy of the light, the energy level of the electron of the molecule gets higher, and the energy level goes back to the original energy level. The electron emits the energy. When the energy is emitted, the energy is transformed into the light. This is fluorescence. And the point is that the wavelength is different when the electron gets the energy and the electron emits the energy. Next, I'll explain you about where the fluorescent substance in citrus is contained. The answer is here. So the fluorescent substance is contained in peel. Here I showed one of the fluorescent substance in citrus. It is called polymethylcycloflavonoid. It's contained in many kinds of citrus in the world. And when the peel got damaged, this substance comes out from the peel. So therefore, we can get the fluorescent image from the from citrus. Next, I'll show you the method of this experiment. First, we prepared this citrus called Caprock Plank as a representative of the Indonesian citrus and divided this into 3 groups. One is sound, the second is the scratched group, which means the swap is swapped with sandpaper, and the third is the brushed one, which means the pressed with lehometer. As you can see, there's no big difference during these 3 groups of citrus. These 3 groups of citrus were kept in the fridge. The temperature was set 25 degrees Celsius, and then we extracted 3.1 grams of peel and mashed and mixed with N-hexane and kept for 1 night. After that, we conducted the spectroscopy by fluorescence spectrometer, and we searched here the absorbance, excitation, and fluorescence wavelengths. Next, this is a stage to get the fluorescent image. We used 4 UV lamps, which wavelength is 355 nanometer, and we take the photo of the image and get the RBG image, and we transform this image into the HSI image. Is because when we use the HSI image, we can change the grayscale. Then, what is the merit to use the HSI image and grayscale? I'll show you the example. This left one, the left one is the RBG image, and the center one is the HSI image, and the right one is the HSI image, which grayscale was changed. As you can see, the left-hand one and the center one, you won't be able to see the big difference of color, but if when we change the grayscale of the HS image, you can see the difference of colors, like here. This is the damaged area detected by fluorescence reaction. Then I'll show you the result and discussion. First, from the extracted pale data, we got 2 spectrum. First is about the absorbance, and the next is about the fluorescent spectrum. We can see 2 big peaks in the absorbance data. The first peak is 330 to the 350 nanometer, and the next peak is the 420 to the 450 nanometer. And about the fluorescent data, the first peak is the 500 to the 520 nanometer, and the second peak is the 740 to the 750 nanometer. So from this data, we can estimate that this citrus contains two substances. And please, sorry. And as I mentioned the first part of this presentation, when consider about the polymethyl flavonoid, which contained in many kinds of citrus, its excitation wavelength is 320 to the 390, and the fluorescence wavelength is 520 to the 570. And when we think the wavelength of absorbance and excitation is equal, we can estimate that this Indonesian citrus also contains the polymethyl flavonoid. And so we can estimate we can get the fluorescent image. This is the image data. So we can clearly see the damaged area like this, So we successfully get the fluorescent data, and we can conduct it. We can conclude that the fluorescent imaging is also useful in the Indonesian case. But can you see the stem part is also have the fluorescent reaction? So this means that the machine may mistakenly choose the sound one as the rotten one. So this is the conclusion. The first is we can use fluorescent imaging for Indonesian orange to detect rotten one, but we need to separate the stem from the damaged area in the fluorescent image. This is the reference. That's all. Thank you very much.
Anyone? Question? Would be good.
Thank you for your presentation. Could you show me method slide? Yes. What is the difference among three pictures?
As I showed the former slide, these three different is the A is the sound one, which means no damage.
No damage.
Yes. This is the left one, and the center one is the scratched, which means swapped with the sandpaper. And the left one is the the right one is the brushed citrus, which means the pressed with the leometer. So as you asked me, we can see the clear difference these three citrus. So we conducted the fluorescent imaging to clearly see the damage.
Okay, thank you.
Anyone else?
Thank you for your presentation, and please show me the number 10 or 12 graph, the result graph. Yes, and at left peak is from the substance. Next picture, please. Yes, and you mentioned the left peak is from polymethylflavonoid. Is it right?
Yes.
Yes. Then right peak is from what causes the right peak? I want to know it.
Okay. I don't know what substances, but we can. I thought we can estimate two substances are contained in this citrus, but in the former paper, this polymethylflavonoid was contained many kinds of citrus, and I thought this case is also in this case in the citrus may contain the polymethylflavonoid.
You think there is another substances?
Yes, I think.
Okay, thank you.
That's all? Did you do this experiment by yourself?
Oh, no.
No? Someone?
Yes, I referred the experiment in Indonesia.
No. That you did.
Oh, I didn't.
You didn't. Someone's this. Who did this?
Oh.
No. No author's name.
Sorry, no author's name.
Okay.
This is reference.
Next time, Pilar Sensei show you how to make a reference.
Oh, thank you very much.
That's all from Kyoto. NTO, please. NTU Professor Suming Chen, please.
Any comments?
Okay, thank you for your presentation. Please show me the grayscale image.
This one?
Okay. How do we prove the white point is the damaged area or it is just noise? How can we prove it?
Oh, how can I prove? Oh. So, you want to know how to prove this is not the noise?
Yes.
Oh. So sorry, I don't know.
Okay.
I'm so sorry.
Okay, thank you.
Any more comments? Okay, that's all from NTU. Thank you.
Scuba people? Anyone?
Thank you for your presentation. I have one question. How much damage of scratch or brush? Like how much damage affect to inside the orange? The scratch and brush is only on skin, right? Skin of orange. But we eat inside, so.
Yes. So I don't know the concrete mechanism, but when the peel is damaged, the bacteria enters inside the orange. So, because of the bacteria, I think the peel is rotten, and the next the inside the orange is rotten. I think.
Thank you.
I have one simple question. What kind of process so seriously damaged by citrus in Indonesia? What kind of process? Harvesting, processing, staging, what kind of process so mainly affects the serious damage to citrus?
Oh, sorry, I couldn't clarify you.
Final target is not only the detection the damage, but also the how to make more smart processing, right? Yes. Yeah, that's my opinion. Thank you.
Oh, thank you very much.
I have a question as well. Do you think this method of image sensing could help with choosing what oranges to export for Indonesia? Will it help with exporting, to choose the good products, or is there another objective for this?
Oh, so you mean this method is applied to another agriculture crops?
Yeah, the practical uses. Is it supposed to be used to detect the good fruits and then make those export those, or has it not developed that way yet?
So you mean this can be
like, what are the practical uses of this, I guess?
sorry. Oh. I think the best timing is before storage. It is because when the lot one and the sound one is storage together, the bacteria may go sound one. So preventing from the spread of the lot one, we need to separate the lot one as early as we can, like before storage.
Okay, thank you.
Thank you for your presentation. Have you? This is just like a comment, but have you ever gotten Japanese researches like that? Because I think Japanese put more importance on its quality of fruit. So, is there Japanese research like that? Research to conduct, detect its quality?
Yes, it is very conducted, and this technology is actually used in Japan already.
Oh, thank you. That's all from Tsukuba.
Okay, thank you very much. Good discussion. As long as I know, this kind of technology is good for save food, because during storage, 30%, 20% fruits would be rotten during stored. So to avoid that food loss, we need this kind of technology. Especially Indonesia, Malaysia, and in ASEAN countries, they have a higher temperature. That's why much amount of food would be spoiled away. So we stop that. That is one of the reasons they are now doing. Okay, thank you very much. Good discussion. That's all today's presentations. And next week we have different menu. That would be the how to write abstract. But just before that, as I mentioned, one more presenter will give us a present. Is there anything else from you? Can we close today? Okay. Okay. So see you next week.
See you.
Bye bye.